moment of inertia. As I said, this is not, it's a little bit away from the topic of this class. It's like introduction to some material that you guys need for the following course, strength of materials. And this moment of inertia is a key factor, everything that has to do with bending. So you will have to deal with that a lot, not only the following course, but for the rest of your life. So we're going to talk about moment of inertia, learn how to calculate moment of inertia, the parallel axis theorem that allows us to calculate moments of inertia of more complicated figures. We will learn here how to calculate moments of inertia by integration of very simple figures, but for more elaborated figures we need the parallel axis theorem. For moment of inertia of composite areas, and we will mention a couple of parameters that are key to qualify sections that are going to be subject to bending, basically beams and columns for buckling. So I want you to watch a very short video about like an introduction to this topic. Let me put it here. I hope it works. I hope it works.
Let's say we have a plank of wood, which we would like to use to cross a canal. It has a rectangular cross-section, and so we can either use it like we have done here, or we can rotate it onto its side, like this. Intuitively, we can tell that the plank will be stiffer if the load is applied to the shorter side of the cross-section. Some cross-sections are much more efficient at resisting bending than others. The further the material is spread from the bending axis, the stiffer a cross-section tends to be. The cross-section on the right has more material located far from the bending axis, and so is better at resisting bending, even though both cross-sections have the same area. This concept of resistance to bending can be quantified by calculating the area moment of inertia, which is also sometimes called the second moment of area. The area moment of inertia reflects how the area of a cross-section is distributed relative to a particular axis, and so is a measure of how much resistance the cross-section has to bending. The I-beam locates the majority of the material as far as possible from the bending axis, and so is a very efficient cross-section. This is why it is so commonly used in construction. It's worth clarifying at this point that the area moment of inertia should not be confused with the mass moment of inertia, which is a parameter used to describe the resistance of a body to changes in rotational velocity. There are similarities in the way the two parameters are calculated, but they have different units and completely different uses. So, when might you actually need to use the area moment of inertia? Well, it is a particularly important parameter for the analysis of beams and columns. This equation, for example, defines the deflection of a beam for an applied bending moment, M. You will notice that the term EI appears in many equations. It is called flexural rigidity. It quantifies the resistance of a beam to bending. As we have just seen, I is the resistance due to the geometry of the beam cross-section, but the stiffness of the beam material also contributes to its total resistance to bending. It is captured by Young's modulus, E.
So this is what we are going to learn how to calculate I, moment of inertia. It's a measurement of how the area or the cross-section of the beam it works to bending. It gives you like a quantification of how good the beam or the cross-section is to resist bending. But not only the cross-section of the beam holds the bending, also the material. It's different if I have a beam made of wood or made of concrete or made of steel. So the shape of the cross-section and the properties of the actual shape, how good that shape is to resist bending, is given by this. And the material is given by this. We won't talk about this here. You will talk about that more in the following course. So we're going to learn how to calculate these two to quantify the goodness of a cross-section to support or to resist bending.
Flexural rigidity also appears in the analysis of columns, where it can be used to calculate the critical buckling load.
That's it. That's what I wanted you to see.
Let's say we have
Okay. All right. So we are going to learn how to calculate moment of inertia. The moment of inertia gives you an idea. Let me write here the equation again. The equation of moment of inertia is that's the equation. Remember the guy said it depends on how, it's like a quantification of how far the area is from the rotation or the bending axis. So if a cross section has a lot of area far from the axis, it's good for bending. And you saw it in that example that he put at the beginning, you understand that this section is much better to hold bending, right? And it's kind of very intuitive. I just an example, if you put load over this one, it bends a lot more and it's going to break it kind of sooner at a lower load than this one. This one is very good at holding bending. And if you make a cross section like this, even better, because it has a lot of area far from the axis. Let me draw the axis of rotation. It will be on the axis of bending. This is the axis of bending. So this has a lot of area far from the axis. Far. This has the area is very close to the axis, so it's not very good. And this one is better than this one, but not as good as this one. So look, this equation multiplies every piece of area of the cross section by the distance of that piece of area to the axis to the bending axis. If I'm talking about this cross section of a beam, what this equation is doing is taking every piece of area here and multiply by this distance to the bending axis. Area times distance, but it's going to be a square because you understand that if we don't put a square, assume this is symmetric, this element will cancel out this element, right? So at the end, the moment of inertia will be zero, right? Because this is in this one, it will be symmetric with respect to this moment of inertia will be zero. So if you put it a square, all the elements that have negative coordinate y, they don't disappear. When you put a square, the negative disappears, right? So imagine that that's the idea why we put the square here. So all the elements come. All the elements of the area come. Right? So that's kind of like a rough explanation of this equation and how it works. And we're just going to learn how to use it, how to calculate area. So let's start by a very simple area. It's just a very simple integral, and you guys are studying your calculus, right? So you're very good at this. So, I don't think this is going to be any problem for you. So let's calculate the moment of inertia of this rectangle with respect to its base. Oh, another very important point about calculating the moment of inertia is the axis with respect to, or the bending axis, the axis that you are going to calculate the moment of inertia with respect to. So you can calculate the moment of inertia of a cross section with respect to this axis, or an axis over here, or an axis here, or an axis here, or an axis here. So the moment of inertia depends on what axis you choose or you are required to calculate. Usually in structural analysis, you study the cross section, the centroidal inertia, so the moment of inertia of an axis that goes through the centroid. But it doesn't mean that you cannot calculate the moment of inertia with respect to any axis. Let's start here for a very simple calculation. I'm going to calculate here the moment of inertia of a rectangle with respect to its base. So this axis. Later we will calculate this one, the centroidal, which is more useful actually. Right? So let's start with this one, which is kind of like the easiest moment of inertia that you can think of. So I'm going to select a differential area. So I'm going to choose this differential area. So it's a piece of area that has all its elements at the same distance from the x-axis. So the distance from that is this. That's the distance from the differential of area. All the elements of this area are at the same distance y. So when we calculate the integral of y squared dA, well, we can do this integral because this y is the same for all the elements of this differential of area. What are the dimensions of this? Well, the dimension of this is d, and let's call this little dimension dy. So dA will be b times dy. Okay, so we're going to calculate y squared dA for all the tiny rectangles that I have in that rectangle as I change y from 0 to h. Right? So I will do the moment of inertia with respect to x will be equal to integral from 0 to h of y squared dA. So it will be integral from 0 to h y squared b dy will be equal to b over 3 from 0 to h equals to 1/3 bh cubed. That's our first moment of inertia. Moment of inertia with respect to x equals to 1/3 of bh cubed. Alright. You have to memorize that. Not really. This is the moment of inertia of a rectangle with respect to an axis that goes through the base, right? Because of this axis, 1/3 of this times this. You want to put dimensions. This is 2 by 4. What is the moment of inertia of a 2 by 4? Well, you just replace. If this is 2. If this is 2 inches and 4 inches, the moment of inertia of that 2 by 4 will be equal to 1/3 of 2 inches times 4 inches cubed. Can somebody do that operation? I don't have it. Anybody? Anybody quickly? Can you do that operation?
64.
What? 64? 64? Wait.
Oh, wait.
Whatever it is.
4 cubed. Oh, my bad.
What is it? Well, I can do it here. 1/3.
43.33.
What?
43.333.
Let's do like this. Inch to the 4. The units are, look, you have this one dimension here and 3 dimensions here, so 4. The dimensions to the 4. That's the units of moment of inertia, dimensions to the 4th. Okay? That's the moment of inertia. You will use it for some stuff later. We are not talking about what is the use of this now. You will see it next course. Okay. Let's do another one. Let's do another one just to practice. Let's do moment of inertia of the same cross-sectional area, but with respect to the centroidal axis, with respect to x prime. This, as I said, is more useful in all structural calculation. This is a centroidal axis. It's called centroidal because it goes through the centroid of the cross-sectional area. So we're going to calculate the centroidal moment of inertia of a rectangle by integration. Let's do that one just to practice. So I have moment of inertia, and I'm going to call it here x prime. X prime. We usually put that prime when it's a centroidal axis to differentiate that axis from any other axis that is not centroidal. The centroidal is called prime in this. Usually we do that. So it will be the integral. What will be the difference here? The difference is that everything is the same except that the limits are from minus h half to h half. Right? We go from minus h over 2, those are the limits of integration, but nothing major, right? So minus h over 2, integral of y squared dA, so it will be integral from minus h over 2 y squared, the differential of area is the same thing, b dy. So it will be b y cubed over 3 from minus h over 2 so it will be equal to b over 3 h cubed over 8, right? Plus this q will be minus h cubed over 8, but with the minus of the integral will be plus, right? H cubed over 8. So this will be equal to d h cubed, and then I will have 2 8s, so 1/4 times 3, 1/12, right? So the moment of inertia, the centroidal moment of inertia of a rectangle when that axis is parallel to one of the sides is equal to 1/12 bh cubed. Okay. That's our second moment of inertia. We have two moments of inertia. Remember what is this equation for? It gives you the moment of inertia with respect to an axis that goes through the centroid and is parallel to one of the sides, right? 1/12 bh cubed. Question?
I was wondering where you got b dy from.
Would it be? Same thing as before? Same thing. The differential of area is the same in this than in this. You're right, let me put it here. This is the differential of area, b dy. Okay? Better? Better?
Yeah.
Okay.
Can you explain why you picked your bound negative h over 2 to h over 2?
If I want to do the integral of y squared dA, I'm going to do this operation for all the area here, right? All the area. So I pick up a differential of area like this one, and I have to do the summation of all these terms for all the differential of areas that I found as y goes from here to here, right? As y starts at minus h over 2, which is this distance. Let me put it here. So this will be this distance is h over 2, right? And this distance is h over 2. The centroid of a rectangle is in the middle. Is that answers your question?
Yeah, a little bit.
A little bit, not completely.
I'm just confused, like, how come you don't start at 0 to h over 2?
Then I will be making the moment of inertia of only this area.
Oh, okay.
In order to sweep the whole area, I have to start y at here and move y all the way to here to sweep the whole area.
Oh, okay.
Right? Clear for everybody? Remember that an integral is just a summation. So we're going to do a summation of what? A summation of this area times this distance squared. And this is just a general area. In order to sweep the whole area, you have to do for this one, for this one, for this one, for this one, for all of them from here to here. So the way to sweep them is to vary the value of y. If you start when y is equal to minus h over 2, that will be this first rectangle here. That's the first one, when y equals h minus 2. And then you add the other one, and then you add the other one, and you go adding differential of area all the way to the top. From this point to this point, when y is equal to minus h over 2, all the way up to the highest point when y is equal to h over 2.
Wait, so why couldn't you just do 0 to h, like the last example?
Oh, because we are calculating the moment of inertia with respect to this axis.
Oh, okay.
In the previous problem, we were calculating the moment of inertia with respect to this axis. So we start here, and y, this is the axis with respect to, you measure the y coordinate. So if the axis is this one, to sweep the whole area, you go from y equals to 0 all the way to equals to h. But now our axis is this one. That's why I have here x prime. The previous one has x. This one is from here to here.
Okay.
Right? Good questions. Good questions. All right. I put this in a rectangle like that because we already did the moment of inertia of a rectangle with respect to an axis that goes through the base. We already did the moment of inertia of a rectangle with respect to an axis that goes through the centroid, which is this one. You see, this is 1 over 12, and the other one is 1 over 3. And we don't have to do it again because we did it already. And if we ever need the moment of inertia for a rectangle with respect to any of these axes, we have it already. Is the formula already?
For the h cubed over some number, is that an 8?
Yes.
Why is it 8?
Remember to evaluate this integral, you have to replace the value of y by h over 2. And the value of minus h over 2. So you replace y cubed here, h over 2 cubed will be h cubed over 2 cubed. This is 2 cubed. Alright? Let me put it here. This will be the I could put here, maybe the best way to put this will be h over 2 cubed, a little h over 2 cube minus h over 2 cube. In order to evaluate the integral, you replace by the limits. You replace the variable by the limits, right? h2 cube minus h2 cube. And then you can get h over 8, h cube over 8, h cube over 8. That's how you get here the h cubed over 8 plus h cubed over 8. Good? Good? Everybody good? Alright. I was saying that eventually you need to, for some reason, the moment of inertia of a rectangle with respect to this axis or this axis. We already have it here. And there are people that tables of basic figures, and so when you need a figure, you first go and look on a table, so you don't have to do the calculation. So there are tables for that. Let me show you one table here. Let's see if I have it here so I can show you without so much geometrical properties. Look. For example, this guy has here the moment of inertia with respect to he called it X. Is the one that we did 112 over BH, 112 BH cubed, right? It's this one here. This guy doesn't have the moment of inertia with respect to this axis. We could put that one here to make this table more complete. And we have moment of inertia of this circular area with respect to this X. Right? So you can go to a table and look at moments of inertia of figures with respect to some axes that people have done before you. So you can go and just take the value, the formula from the table and use it. Right? If we are doing our own table, well, we only have two values for that table. This one and that one. We can start our own tables. We have two values already. Okay. Let's do one more. I guess one more will be enough. Eventually, if we have time, maybe next class we can do one more. But let's do this one. We are going to calculate the moment of inertia of this triangle with respect to the base. Oh, before that, can you imagine what happened if somebody asked you the moment of inertia of this rectangle? Let me erase all this garbage here. What happens if somebody asks you the moment of inertia with respect to would you be able to calculate the moment of inertia of that rectangle with respect to that axis? It's basically the same problem that we did, but we rotated like that, right? So in this case, the equation will be this same equation, but instead of B will be H and H will be B, right? So this will be the moment of inertia with respect to Y prime will be 112 H EQ, right? You get that, right? We don't have to just do the whole procedure by rotating and putting BH. It will be exactly the same, right? All right. So keep that in mind. So this is a general formula, and you can use it for this. And if you swap this, then you are using this one, right? Be careful which one goes to the cube. The term that goes to the cube is the term that is perpendicular to the axis, and the term that goes in the first power here is the one that is parallel to the axis. This B is parallel to the axis with respect to, actually we are working with this axis, right? So B H cube will be B H cube. Now that we are working with this axis, the side that is parallel to this axis is H. So H goes to the first power, and the one that is perpendicular goes to the cube. So be careful with that. Right? Okay, let's do the triangle and then we can move on. Okay, so how can we do this triangle? We are going to calculate the moment of inertia with respect to the x-axis. So we're going to choose a differential of area like this. The trick for this differential of area is that all the elements of the differential of area are at the same distance from the axis. is y. Right? And then this distance we will call it dy, and then this will be x. This distance will be x, where x and y can be understood as the coordinates of this point. That way we have very well localized the differential of area. The differential of area is this red rectangle that is a distance y from the axis. So as soon as I choose different values for y, I'm sweeping all the area of the triangle. And this x will be the x coordinate of this point. So if I set up the equation of this line, I have this differential of area well defined, just by assigning values to x and to y. So what is the equation of that line? That equation will be negative h over b x plus h. All right? So what is the area of the differential of area? What is it? What is the area of the red rectangle? This times this, right? X
dy.
times dy. That will be the area of the little red rectangle. X dy. Right? So now we want to calculate the moment of inertia with respect to h to x, which is the integral when to sweep all the rectangles that I obtain when I change the value of y from 0 to h, right? So the limits will be 0 to h. And the formula is y squared dA. That's the formula for moment of inertia, right? So in this case, now I replace for y squared, and dA is x dy, right? If I solve that integral, I can get the moment of inertia with respect to x. Remember, all we are doing is just to do the summation of this area multiplied by this distance squared for all the areas that I can find along the whole area of the triangle, right? That's what we are doing. Nothing mysterious, just a summation. But we do this dy very little, so it's tiny rectangles. We have a problem with the x, right? We cannot integrate with that x. We have to put x as a function of y. I hate that. It's horrible. So from here, so we have to solve for x. So we have h over b x equals to h minus y. So from here I will get x equals to b over h minus y, I guess. So we can put this value of x into our integral. We will get integral from 0 to h of y squared x. X is b over h minus y dy. Right? So we continue here. Integral from 0 to h. So what do we get here? B, maybe b over h can go out, right? B over h. I have here y squared h minus y cubed because of the surgery, I'm so busy to still. Did I do it right? Okay, if I make a mistake, it's your fault. Okay. B over H, then I have here what H y cube over 3 minus y 4 over 4 from 0 to H. Good. So then I will have B over H. I replace the limits, right? I replace y by the limits H and 0. So H times H cubed over 3 minus H 4 over 4. And then what do we get? B. Okay, I can cancel 1H with 1H and 1H here, right? So I have B H cubed 1 over 3 minus 1 over 4. So this will be BH cubed 12 4 minus 3, so 1. So that moment of inertia of the triangle with respect to the base is 1, 12 BH cubed. Okay, we have another one. Oops. Okay, now we have another moment of inertia. Moment of inertia of a triangle with respect to an axis that goes through the base. If you want the moment of inertia of a triangle with respect to this axis, instead of this one, you just swap here, right? HB cubed, right? No problem with that, right? Problem with that? No problem with that? Problem with that? No problem. Okay. I would like to do, no, I really don't like, I don't want to do, but the next step will be calculate the moment of inertia of the centroidal axis of the triangle. I don't want to do that. The integral becomes so ugly because it's from minus h there to plus 2 and these killers here. So then it comes the parallel axis theorem that I mentioned to help. Parallel axis theorem. Let's look at that one because it's super useful. Well. Parallel axis theorem. Basically, let's do a little thing in here. If you have any figure, and this is a centroidal axis, and this is another axis, any axis parallel to that one, and they are separated by a distance d, right? If this is an element of area dA, this will be the distance y prime, and this will be the distance y, right? So the moment of inertia with respect to the x-axis will be equal to integral of y squared dA, right? Right? And y is equal to y prime plus d, right? This is equal to y prime plus d. So then we can write this as y prime plus d squared times dA. So this will be integral of y prime squared dA plus 2 integral of y prime dA plus d squared integral of dA, right? Everybody follows? Nobody got lost? I just expanded this, right? This is y prime squared plus 2dy prime plus b squared, right? And that's what we have here. Okay, let's see what we got.
Professor,
Okay.
shouldn't the middle integral have a d then?
No, it's the
Why?
first one is this one. Oh yeah, it has a D. It has a this. Yeah, it has a D here, right? So right. Yes. Yeah, this little D. That one.
Yeah.
Okay. Yes. Okay. What is this? What is this? This is the moment of inertia of an area with respect to the y prime axis, right? So this is the moment of inertia of this figure with respect to this axis. I said y prime, x prime. This is the moment of inertia of that figure with respect to the x prime axis. Right? Right? So I am trying to calculate the moment of inertia with respect to x, which is y squared dA. If I have y prime squared dA, this is the moment of inertia with respect to this axis, not this one. This is this one. This is this one. You see the form of the formula? You see? Got it? No? This is the moment of inertia with respect to this axis. This is integral of y prime squared dA. I can put it here. I probably have that here somewhere. I have it. No, I don't have it here. But I have it here. I erased it. I erased it. Is this clear that this is the moment of inertia with respect to this axis? See, y prime. So this times dA. So let me put it here. This is I x prime. What is the integral of dA? A. So this is a d squared, right? And what is this? Actually, just this part, y prime dA. Let me something here. 1 second. Let's analyze what is this integral of y prime dA. You just went over the calculation of centroids. Remember, the calculation of centroids was y bar equals to integral of y dA divided by integral of dA. That's what you just saw on the video that I got you to see, right? So this equation will give you, let's say you were trying to calculate the moment of the centroidal of this figure, and this is the x-axis, and you want to calculate, say the centroid is over here. This distance we call it y bar, and you use this equation to calculate the distance y bar, right? What happens if you calculate the distance of the centroid with respect to an axis that goes through the centroid? What do you get? If you put this axis here, what do you get for y bar? 0, right? So what this is doing is kind of the numerator of the equation that gives you the centroid when the axis is going through the centroid. So you're gonna get a 0 here, you're gonna get a 0 here, this is gonna be 0 divided by the area. But we don't care about this here. This is gonna be 0. This is the area of the figure, which is not 0, so it's, in order for this expression to be 0, the numerator has to be 0. Right? So this integral this integral is the integral that you would use to calculate the centroid of a figure when the axis of reference is going through the centroid. So this integral is 0. Right? So this will go to 0. Okay? So we just found then that the moment of inertia with respect to an axis, the moment of inertia with respect to an axis that is parallel to another axis that is centroidal, that's what I call it prime. Maybe it would be a good idea to put here the centroid. This is the centroid, right? The moment of inertia of a figure with respect to an axis that is parallel to the centroidal axis is equal to the moment of inertia with respect to the centroidal axis plus AD squared, where d is the distance between those two axes. Okay? Got it? Can we go on? Yes. Correct? Everybody? The moment of inertia, when you have two parallel axes, one of them goes through the centroid, the moment of inertia with respect to the other axis is equal to the moment of inertia of the centroidal plus AD squared. The moment of inertia with respect to this axis is equal to the moment of inertia of this axis plus AD squared. Let's do a quick example with what we just learned so we see. Remember that we found the moment of inertia of the rectangle with respect to the base, and we found 1/3. We found this value here. Let's put it here. Let's do this here a little bit up. This is 1/3 BH cubed. The moment of inertia, right? And this is this is x prime. This is x prime. We found this to be 1/12 BH cubed. That one we have it here. You see it, 1/12? See it? Okay. So we're going to do it not by integral, but using that equation. We know that Ix is equal to Ix prime plus AD squared. That's the equation that we just found. So let's calculate this one using this one. Okay? I'm going to calculate Ix using this value to see if I arrive to that value, to see if I arrive to this value. Based on this, I use this equation to find this. Let's see, we got the 1/3. So Ix will be equal to Ix prime, which is 1/12 BH cubed plus AD squared. What is the area of that rectangle? The area of the rectangle. Who is awake here? BH. No, it's BH. No, it's B. BH, sorry. BH. That's the area of the rectangle. Times the distance. What is the distance between those two parallel axes? H/2. Squared. So this is equal to 1/12 BH cubed plus BH, H squared, and this is 2 times 2 times 2, 8. So this is equal to BH cubed 1/12 plus 1/8.
Why is it 1/8?
What?
Isn't 2 squared 4?
Oh, yeah, 4. Thank you. 4. So what do we get here? 1/4 is the same as 3/12, right? So this is BH cubed, and this will be 12, 1 plus 3, right? So what is 4 over 12? Is not 1/3? Is it? Is it?
Yes.
1/3 BH cubed. Look, we got it, right? We got it. We found this value. So it's like a little proof that parallel axis theorem works. Look, you see what we just did here? We calculate this moment of inertia based on this moment of inertia by using the parallel axis theorem equation. Basically, you get the centroidal inertia, you add AD squared, and you get the moment of inertia with respect to another axis. Parallel. The only condition is that they have to be parallel. It doesn't have to be here. You can calculate with respect to an axis here, anywhere. As long as it's parallel, you can calculate the moment of inertia with respect to an axis over here. As long as you know the distance, you calculate, let's say this is axis x3. The moment of inertia with respect to x3 will be equal to the moment of inertia of this axis times area multiplied by this distance squared. Okay? Easy. So now you can calculate many moments of inertia. You need the centroidal. That's why the centroidal is also very important. If you know the centroidal, you can calculate any other. Parallel. Let's see. Good up to that point. Let's do another example. Remember that we were working with the triangle? And I say, who wants to calculate the moment of inertia of the centroidal axis of the triangle? Oh, horrible, that integral is so difficult. So let's do it using parallel axis theorem. So using parallel axis theorem, let's see what I can do a little space here. So what I'm going to do now is this triangle. Let's copy this triangle. Paste. Okay. Let's erase some garbage here. So we found that the moment of inertia with respect to x, we got that to be 112, right? Remember? The moment of inertia with respect to x, this one, is 112 dh cubed. 112 dh cubed. Now I want to calculate the moment of inertia of this with respect to a centroidal axis. Let's put it here. This will be x prime. Okay? So my formula for parallel axis theorem is Ix equals to Ix prime plus AB squared. In this case, we're going to find this one, right? So we have to solve for that one. Actually, the centroidal is equal to the other one minus AB squared, right? Agree? So in this case, I am calculating this one, not the one outside. So what is Ix? We just have it here. Is 112 BH cubed minus area. What is the area of the triangle?
1/2 HP.
Somebody else? Yes. Why don't everybody should say it? Just a choir of people hearing different voices. It would be nice. A nice 112 BH, like that. Multiply what is the distance between those two axes? Everybody. No.
Over 3.
H over 3. Right, it's a triangle. So multiplied by h over 3 squared. Okay.
That goes over the center of mass.
The centroid, right? This is h over 3. We are calculating the centroidal moment of inertia of that triangle. The moment of inertia with respect to an axis that goes parallel to the base and goes through the centroid. So let's do this. Let's do this. So this will be dh cubed 112 minus 1/2 27? No. Is it? Oh no, it's just a square. 9. Right? You are the one that checks my arithmetic. Don't get asleep. So this is dh cubed 112 minus 1 over 18. So this will be dh cubed. And then here we can do what? 36? 3 minus 1. So 1 over 36 bh cubed. So we have another formula. Yeah, another formula for our warehouse. X prime equals 1 over 36 bh cubed. Another formula for our okay. Let's check with maybe this guy has that value in this table. Remember, 1 over 36 for the centroidal, 1 over 12 for the side. Let's see if it has a triangle here. Look here, it has a centroidal of a triangle. 1 over 36. Doesn't have you can find different tables of this on the web or in any book. Doesn't have one with the moment of inertia of what? Alright. Okay. Let's see if we can at least start another problem. Got this one? Questions? Good?
Can you explain the h over 3? The distance from h?
This is the distance. This is the centroid of the triangle, right? And this is the location of the centroidal of the centroid of a triangle with respect to the base here. Is 1/3 here and 2/3 here.
Okay.
Remember?
Yeah.
We saw that before, like a month ago, and you guys just reviewed this in the last class. Right? Okay, let's do one. Let's start one more example. Because there is no more. I can wait in 4 minutes. Let's do. This example. How do you do the moment of inertia of this figure with respect to x-axis? Actually, it says here x and y. Determine the moment of inertia of the I being shown with respect to x and y axis. Let's start with the x-axis, which is more difficult. The y-axis is so symmetrical, so it's much easier. So what would you do here? The best thing to do here is to break this into 3 figures, actually 3 rectangles, and we know the moment of inertia of a rectangle with respect to the centroid. We just move it with the parallel axis theory to wherever we want it. So I will break this into these three rectangles. I call it 1, 2, and 3. So I will say the moment of inertia of this figure with respect to the x-axis is going to be equal to the moment of inertia of figure with respect to the x-axis of figure 1 plus the moment of inertia with respect to x of figure 2 plus the moment of inertia of with respect to the x-axis of figure 3. How do you do moment of inertia of figure 1? Well, you do it using the let me put it here. So I cannot put it here. The moment of inertia of figure 1. Well, you calculate the moment of inertia with respect to the local centroidal axis here. Let's call it x1 prime. And then you move it with AD squared. Let's call this distance d1, right? So then you will have that the moment of inertia with respect to the x-axis of figure 1 is the moment of inertia of the figure 1 with respect to x prime 1 plus area 1 d1 squared, right? Right? So what I'm doing is calculate the moment of inertia of this little rectangle with respect to the centroidal of the little rectangle, and then move it down here to this axis by adding AD squared. Okay? Clear? And what is the moment of inertia of a rectangle with respect to the centroidal axis? Do you remember? Well, I have to scroll. Oh, it's not. Oh, yeah, where is it? Oh, my God, very up. Here, 112. Moment of inertia of the rectangle with respect to x prime. 112. 112 dh cubed. 112. So this one is equal to 112. What is B for that little rectangle? For the little rectangle, B is 24. 24. And what is H? H is 6. 6 cubed. Plus the area. The area is 24 times 6. Times the distance squared. The distance d1 squared is the distance from this axis to this one. So it's going to be 3 for half of 6 plus 48 plus 6. Right? That will be 6 over 2 plus 48 plus 6 squared. Then you have the moment of inertia of figure 1 with respect to the x-axis. Is that clear? The second, the number 2 is the same. Number 2 is the same. This one, you can do the same thing in the number 3, so you finish this. Number 3, you can also do the centroidal here, right? And then move it this tiny amount to go to x, right? Or remember that we already found the formula for the moment of inertia of a rectangle with respect to the base here. So you can use that one, right? It's just 1 over 3 dh cubed. And you don't need to do the summation of the AD squared. If you want, let me put it here so we can leave. This one you can use directly. Moment of inertia with respect to x of figure 3 is equal to 1 over 3 dh cubed. So 1 over 3, 48, 6 cubed. In that one, you don't need to use parallel axis theorem because you already know the formula to calculate the inertia with respect to this axis that goes through the side, right? In this one, you don't need it because you don't have the moment of inertia with respect to an axis that goes outside of the rectangle. So you get the centroidal here. I will call this axis x2 prime, and then I will call this distance d2 in order to calculate, using the parallel axis theorem, the inertia of this one. So this and this. Okay? Make sense? Make sense? Make sense? Good. Okay, so I'll see you guys on Thursday. Yes.